Welcome to Math 1400. This is Nunez Community College. Today's section is section 1.1 and it is radian and degree measures of angles. So we need to first of all talk about an angle. What is an angle? Well, an angle is two rays joined at one endpoint. Two rays joined at an endpoint. Now, we are looking at an angle. There's our two rays, and we're going to have a little arc in between, and we'll have a designated angle variable symbol. We'll call that angle theta. The parts of the angle are the two rays. We start where there's no arrow. We call that the initial side. And then we go to where the arrow is pointing. This is called the terminal side. And the point at which they're both joined is called a vertex. An angle we're going to look at, most of them are drawn in something called standard position. An angle in standard position is an angle that's on a coordinate plane. An angle that's on a coordinate plane. And the thing that is special about them is the vertex is always at the origin. And the initial side is always going to be the positive x-axis. The positive x-axis. The terminal side can be anywhere else, but the initial side has to be the positive x-axis and the vertex has to be at the origin. We can then write the angle symbol, which in this case is theta, and that would be an example of an angle that's in standard position. We have angles that look like this, which we call opening, okay? It opens in this direction, which is counterclockwise. So we call that positive angles. That's my angle symbol. It opens in a counterclockwise direction. Counterclockwise meaning going against the clock. When we used to have clocks with hands, it would go against the clock. A negative angle is the opposite. It opens clockwise. So this would be an example of a positive angle opening counterclockwise, and an angle that would be negative would just open in a clockwise direction or with the clock. This is my symbol that I'm going to use most of the time called theta. Other symbols that we use for variables for angles could be alpha and even beta, but I'll stick to alpha and theta right now. Okay, we have angles that are in standard position can be lying in particular quadrants. And it's going to say, where does the angle lie? And we're going to have an angle in standard position. And suppose this was my terminal side. This angle theta would be said to lie in quadrant 2. So it would be a quadrant 2 angle. The angle lies in whatever quadrant that the terminal side is in. Example, this would be a quadrant 4 angle. Again, the terminal side is in quadrant 4. It doesn't matter whether it's positive or negative. It just matters where the terminal side lies. This would be a quadrant 2 angle. By the way, we use Roman numerals to show. And this would be a quadrant 3 angle. We'll call that beta. That would be a quadrant 3 angle. So what happens if it says what quadrant does the angle lie, or where does the angle lie, if the terminal side happens to be on one of the axes? Suppose we have this angle right here, where it lies on the positive y-axis. If that's the case, it's just called a quadrant angle. It's just called a quadrant angle. So if the terminal side is on the positive positive y, the negative x, or the negative y, it's just said to be a quadrant angle. But if the terminal side lies in one of the quadrants, it's called a quadrant, whatever quadrant the terminal side lies in, angle. We now have to look at the types of angles. The types of angles. The types of angles are determined by the size of the angles. By the size of the angles. So the first angle that we have, size-wise, is going to be the smallest of the angles. We will call that an acute angle. An acute angle. An acute angle is an angle that is greater than 0 degrees. I'll put it as theta. But it's less than 90 degrees. So an acute angle is an angle that's between 0 and 90 degrees. The next angle on our list is going to be a right angle. A right angle is when theta equals 90 degrees. By the way, this would be an example of an acute angle. This would be an example of a right angle. Right angle has the little box. Always shows that it's equal to 90. Next we have an obtuse angle. An obtuse angle. Obtuse angle is an angle that's greater than 90 but less than 180. So theta is greater than 90 but less than 180 degrees. And finally, we have something called a straight angle. And a straight angle is when theta equals 180 degrees. The obtuse angle could look like this. And the straight angle is a straight line where we do have a vertex and we show that it is 180 degrees. 180 degrees. All right, next thing up is something where we have an angle that is within a circle. An angle that's within a circle, and the specifications are that the vertex is the center of the circle. The vertex is the center of the circle. So if we have an angle where the center of the circle is the vertex, then that is called a central angle. Central angle. So it's an angle where the vertex is the center of a circle. So we may have this circle, the center is the vertex, and the radius, or the two radii, are the legs of the sides. This angle, angle theta, would be a central angle. Again, within a circle, the center is the vertex, and the radii are the sides. The next thing we're going to have is something called coterminal angles. Coterminal angles. Co meaning two, terminal meaning share a side. So it's two angles that share a terminal side. Two angles that share a terminal side. So I might have this as angle theta, and the coterminal angle with this could go backwards and have the same terminal side. Or I could have two coterminal angles where one would be like theta, and the other one could still be a positive angle, but it may go all the way around and then come back to touch the same terminal side for alpha. So when we're looking at that, and we're looking at coterminal angles, in order to find it, the angle that's negative, or the angle that's, the negative angle is theta, our angle we start with, minus 360 degrees. Because 360 minus the theta gives us alpha. On the one that's positive, it's going to be theta plus the whole thing, 360. So that right there is our coterminal angles. If you're looking for the negative angle, it's minus 360. If you're looking for the positive angle, it's plus 360. So in general, we'll say theta plus or minus 360 degrees is the coterminal angles. Theta plus or minus 360 is our coterminal angles. That's in the degree, measurements. That's in the degree measurements. We also have something called a radian. So let's talk about that. On the unit circle video that I did, we showed the radians, and that's how we're going to get where we're at. But yes, radians is another form of measurement. It's another form of measurement. So we measure angles in degrees, and we measure angles in radians. Now, the most important thing I have to say here is if we're doing any type of formulas, all of the formulas that we use in trig are in radians. So you got to learn the radians. So what exactly is a radian? 1 radian, okay, is when we have a central angle, okay? We have a central angle where we have our radii, or radius. We have theta, which is our angle, and we're going to have the length from the initial side to the terminal side. This is known as S, or our arc length. So this is the length of the arc from here to here. 1 radian is the angle measure, so it's actually theta. It's the angle measure that occurs when the arc length and the radius are equal to each other. So when the arc length equals the radius. Okay, when the arc length equals the radius, that's considered to be 1 radian. That's considered to be 1 radian. Now, here's something that's, I think, an interesting fact. We have our circle, okay? We have our circle. It's on a coordinate plane. And we're looking at 1 radian. Okay, so the arc length and the radius are the same. We're looking at another radian. And we're looking at a 3rd radian. And if we go here, we'll look at another radian, another radian, and another radian. But for right now, I want to just look at the top half here, the top half. If we look at it, there's a little gap right here where we go this radian plus that radian plus that. There's still a little gap right here. This gap is actually 0.14 of a radian. 0.14 of a radian, which means that a half of a circle is 3.14 radians, otherwise known as pi. Pi. So when we deal with radians, we're going to have pi in our answer. So pi being 3.14, it came or it's derived from the radian. And how many radians does it take to make the circle? So instead of using the decimal form, they use this as pi radians, and a full circle is going to be 2 pi radians. Again, we looked at on another video the unit circle, and we did the unit circle in radians and in degrees, the 2 units of measurements that we have. So the next thing that we have up is going to be finding coterminal angles in radians. Finding coterminal angles in radians. So one angle that we're going to have may be this here. Let's say it's pi over 4. That's my theta, pi over 4. We want to find the coterminal angles with pi over 4. One's going to be the angle going backwards. And just like we said here, theta minus 360. Well, instead of 360, radians is 2 pi. So it'll be theta minus 2 pi to find the negative angle. In this case, theta is going to be pi over 4 minus 2 pi. In order to do this, we have to have common denominators because we're subtracting fractions. So it'll be pi over 4 minus 8 pi over 4, because 8 over 4 represents 2. So therefore, we get what? Negative 7 pi over 4 as our angle that is coterminal with theta. That's the negative coterminal angle with theta, negative 7 pi over 4. If we decided to go with the positive angle, or the one that goes completely around and then keeps on going, the positive angle, if I can go the right way, then it's going to be what? Theta plus 360, or theta plus 2 pi. In this case, we'll have pi over 4 plus, we've established that it's what? 8 pi over 4 to give me 9 pi over 4. That would be the positive coterminal angle with pi over 4. So the coterminal angles, if it's in degrees, it's plus or minus 360. If it's in radians, it's theta plus or minus 2 pi. That's how we find the coterminal angles. Okay, the next thing that we have up after that is going to be converting. Converting from one to another. So we're going to convert from degrees to radians, and we're going to convert from radians to degrees. Pardon me for a second while I try to clear some of the board. Not the greatest of technology, so. So when converting from one to another, whether it's degrees to radians or radians to degrees, we must use an equivalent. We must use an equivalent. And that is something where I know that the two values meet up, but they're different numbers. For instance, at 180 degrees, or half of a circle, I know that that is pi radians. So that right there is my equivalent. I know that on a circle, this is 180 degrees, and at the same spot, it's pi radians. So I know that pi equals 180 degrees. And we're going to use that in order to convert. So if I want to convert from degrees to radians, I'm going to multiply by pi over 180. Since they're both equivalents, it's almost like multiplying by a form of 1. So I multiply by pi over 180 because I want a pi in my answer, and radians has pi. So I'm going to look at it, and suppose I'm looking at 30 degrees, and I want to convert that from degrees to radians. I multiply by what it says, which is pi over 180, giving me what? 30 pi over 180. Cancel out the zeros. 3 and 18 simplified to pi over 6, 1/6. If I do that with another number, suppose it's 135 degrees, multiply by pi over 180, 135 pi over 180. 135 and 80 simplified to 3 pi over 4. If it's a negative number, it just stays negative. Suppose I have negative 120 degrees. When I looked at that as in multiplying by 180 and pi over 180, which is negative 120 pi over 180. Cancel out the zeros, and 12 and 18 comes down to what? Negative 2 pi over 3. Negative 2 pi over 3. Now, if I want to go the opposite way, and I want to go from radians to degrees, we multiply by the same exact equivalent, but the inverse. So we multiply by 180 over pi. And the best way to think about it is if you're trying to go 2 radians, you want pi in your answer, so you want to put a pi in it. If you're trying to go from radians to degrees, you want to get rid of the pi, so you put a pi in the bottom so you can cancel them out. So if I have, let's say pi over 2, and I want to convert that to degrees, then I'm going to multiply by 180 over pi. Pi's would cancel out, giving me 180 over 2, which is 90 degrees. 90 degrees. Suppose we come up with something like convert from radians to degrees, but there's no pi in it. Suppose it's just the number 2 radians. If it's 2 radians, we do exactly what we say, exactly what we have here. It's going to be multiply by 180 over pi, which is going to be 2 times 180, which is 360 over pi. But we're not going to leave our answer in that form. It's 360 divided by pi, which is going to give me a decimal. It's going to be approximately 114.5 degrees. 114.5 degrees. And that's how we convert from degrees to radians and radians to degrees. Multiply by pi over 180 or 180 over pi. All right, converting next, we have something called the arc length. We have 4 formulas that are coming up. So we're going to look at the 4 formulas, and then we're going to see what we have to do in order to use them. The first one is the arc length. The arc length is what we saw when we were dealing with the radian. The arc length is part of the outside of the circle. Part of the outside of the circle. So the arc length, we have our circle, right? Our central angle, and that's my theta. This is my radius, and the arc length is the S. There's a formula to find the arc length. It's S, the arc length, is equal to theta times the radius. Just remember, theta is in radians. Theta is in radians, always. That's the first formula. The second formula that we have is going to be the area of a sector. Area of a sector. This part right here that looks like a little piece of pizza is a sector. So we're going to actually find the area of the sector. Shading it in. Using this right here to find the area of the sector, it's going to be the area is equal to 1/2 of the radius squared times theta. Again, theta is in radians. Theta is in radians. So these are two of the formulas that we're going to be using. We also have something called the linear speed. Linear speed, meaning speed in a straight line. If you're in your car and you're going 70 miles per hour down the highway, then your linear speed is 70 miles per hour. As in 1 hour, if you keep on going that speed, you'll reach 70 miles. So the linear speed, which is velocity, is equal to distance over time. But we're taking circular distance and putting it out in a linear path. So it's like the wheels are turning, but as the wheels turn, the car moves forward. So this velocity, which is a distance over time, this distance is the arc length. Because as the wheel turns, then the car moves. So we're taking the circular and we're putting it in a line. So it's the arc length over time. It's the arc length over time. And finally, the last of the formulas that we're going to have is going to be the formula which is talking about angular speed. Angular speed is going to be the speed that the tire, or the speed that the circle is actually rotating. The speed that the circle is rotating. So that's called angular speed. So the angular speed is going to be omega, which is a Greek letter, and it's equal to theta, the angle, how much it turns over time. It's the angle over time. The angle over time. So some of the questions that we may be looking for, let's go back to arc length here. And it might say something like, a circle has a radius of 4 inches. A circle has a radius of 4 inches, so we'll put 4 inches. And passes through a central angle of 135 degrees. Passes through a central angle of 135 degrees. They are going to say, find the arc length. So we're going to come up to our formula, and we're going to plug the stuff in. S equals what? Theta, 135 degrees times 4 inches? Not quite. This is in degrees. We have to put it into radians. And from looking at what we did before, 135 degrees is 3 pi over 4 radians. So that's what we must put in. S equals, I can cancel out the 4's, 3 pi inches is how far it went. And that is approximately 9.42 inches. Approximately 9.42 inches is how much it traveled for 135 degrees through that. Okay, looking at one from a area standpoint, we may have a sprinkler on a golf course. Sprays water on a distance of, over a distance of 70 feet and rotates through an angle of 120 degrees. Sprays water a distance of 70 feet and turns through a distance of 120 degrees. They want to find the area of grass that's watered. So the area of the sector. Again, just like the other one, they're going to keep on giving us the angles in degrees. We're going to have to change them over to radians. So I have area is going to be equal to 1/2 of what? 70 feet. And we're going to square it. And then times theta, well, 120. Theta is going to be what as a radian? Theta is going to be what? 2 pi over 3. 2 pi over 3 radians. So we have what? Area equals, was it the right thing? Yes, 2 pi over 3 radians. So what do I have here? I have the 2 at the bottom and the 2 at the top. They can cancel out. 70 squared is 4,900, and that's feet squared. Pi over 3. And when I take 4,900 multiplied by pi and divided by 3, my area is 5131, and that is feet squared. Well, this is the end of section 1.1. I'll give another video on the linear speed and angular speed as a problem, but most of us won't have to worry about that. And I will see you at the next one.